Choke valve design, steam desuperheating, and severe service control. Steam desuperheating valves in high-pressure steam systems requiring simultaneous pressure reduction and temperature control, specially engineered valves with integrated water injection are used. These valves inject water internally into the steam stream, enabling desuperheating without separate quills or injection devices. The internal injection mechanism must ensure uniform water dispersion and vaporization to prevent thermal gradients, water pooling, or downstream pipe erosion. Injection ports are typically located within the valve body, carefully positioned to promote mixing while avoiding direct impingement on metal surfaces. These valves must maintain accurate modulation across a wide operating range and remain stable under fluctuating load conditions. Only purpose-built desuperheating valves from qualified manufacturers should be selected. Their suitability depends on factors such as steam velocity, injection pressure differential, and turndown ratio. Design approval by the principal is required to confirm performance and long-term reliability in the specified service. Choke valves for severe erosive or multiphase flow. Choke valves are critical components in oil and gas production systems, particularly at wellheads or high-pressure separators, where flow control must be maintained under erosive, multiphase, or cavitating conditions. Gas choke valves must withstand the full closed-in pressure of the well and be capable of modulating flow precisely across varying pressure and flow conditions. The body must be oversized to reduce internal velocities and minimize erosion. Internals must be fully removable without disturbing the actuator or pipeline connection, supporting rapid trim changes using standard hand tools. A two-stage trim philosophy is often applied during early well life. A durable but forgiving stellite or similar material is installed initially to handle debris such as sand or scale. Once well output stabilizes, this trim can be replaced with a more brittle but erosion-resistant tungsten carbide set for long-term operation. All gas choke valves must meet Class 5 or VCS shutoff standards and should incorporate noise reduction features when operating under high differential pressures. Plug and seat components must be designed for repeatable tight shutoff and include guided motion to prevent vibration or misalignment. For high-pressure liquid drains, liquid choke valves are used. These valves typically feature dual discs, one fixed, one rotatable, each containing offset orifices. Flow is throttled by rotating the discs to vary overlap, creating a controlled path for pressure reduction. Most of the pressure drop is shifted downstream to a hardened bean or restriction element to protect valve internals. A protective upstream filter must be included to prevent large solids from damaging the rotating disc mechanism. All wetted components, especially discs and beans, must be made of tungsten carbide or equivalent wear-resistant materials. Modular construction is essential so that any subassembly, trim, bonnet, actuator can be replaced without breaking process connections. Whether handling gas or liquid, choke valves are engineered for high reliability, tight shutoff, and maintainability in some of the harshest operating environments in upstream production. Proper design selection is critical to ensuring long service life and safe operation under demanding pressure and erosion conditions. Control valves for special applications. Low temperature service. Control valves used in applications with design temperatures between 0 degrees Celsius and 150 degrees Celsius must be constructed with materials and packing systems rated for low temperature resilience. Additional care is required in selecting actuator components, sealing materials, and lubrication-free packings that remain flexible and effective at low temperatures. Extended bonnets are typically required to maintain the packing temperature above the minimum service threshold. For services colder than 50 degrees Celsius, cryogenic compatible construction is mandatory. This includes the use of stainless or nickel alloys, extended bonnets long enough to position the stuffing box outside insulation boundaries, and provisions to prevent frosting or ice accumulation that could obstruct valve operation. All such valves must pass dedicated low-temperature performance testing prior to service. Vacuum service. In systems where the process pressure falls below 1 bar absolute, control valves must be designed to handle external atmospheric loading without risk of body collapse or leakage. This includes selecting pressure-retaining components that maintain integrity under vacuum and ensuring that seals, gaskets, and bonnets do not allow air ingress. Surface finish and material compatibility with outgassing requirements must also be confirmed. Special consideration must be given to stem sealing systems to prevent fugitive emissions during vacuum cycles. Steam service control valves used in steam lines rated at ASME Class 300 and above must be constructed with attention to thermal expansion, sealing integrity, and corrosion resistance at high temperatures. Packing must be capable of retaining sealing force across a wide temperature gradient, often with spring-loaded designs. Metal-to-metal seating and hardened trims are standard, and the actuator must withstand radiant heat exposure or be installed with thermal shielding. The valve body must accommodate high velocity and flashing steam conditions without vibration or erosion. Hydrogen service. For hydrogen applications with a partial pressure above 7 bar absolute, materials must be carefully selected for resistance to hydrogen embrittlement. Welds, bolting, and pressure-retaining parts must be compatible with high diffusivity gases, and trim clearances must be designed to limit leakage or fugitive emissions. Stem seals and packings require materials that prevent hydrogen permeation. Any valve in hydrogen service must also consider leakage detection and fire protection measures due to the gas's flammability. Hydrofluoric acid, HF, service. HF acid is highly corrosive and toxic, demanding stringent valve design. Internal wetted components must be made of HF-resistant materials or protected by full-body linings. Tight shutoff and leak prevention are critical, so bellows seal arrangements with backup packing are often required. External hardware must be shielded or coated to prevent degradation by HF vapors. Isolation and handling procedures must follow strict safety protocols, and valve suppliers must demonstrate specific experience in HF service design. Oxygen and high-pressure air service. Any fluid containing more than 21% oxygen by volume or compressed air above 50 bar gauge is considered oxygen service. Control valves for this application must be degreased and cleaned to oxygen service standards and assembled in clean environments. All wetted components must be free from hydrocarbon contaminants to prevent ignition risk. Materials must resist combustion, and non-metallic parts must be oxygen compatible. Construction must ensure smooth internal surfaces to minimize particle generation and ignition points. Ethylene oxide service. Ethylene oxide is highly reactive and flammable. Control valves for this application must be free from dead legs, sharp corners, or surface imperfections that may cause localized reaction or decomposition. All wetted materials must be chemically compatible and non-catalytic. Seal designs must limit crevice formation and allow easy cleaning. The actuator and body must also be designed to contain high energy release in case of internal ignition. Chlorine service. Chlorine is corrosive in both dry and wet forms and reacts violently with many lubricants and organic materials. Valve bodies and trims must use compatible corrosion-resistant materials such as monol or Hastelloy, or must be fully lined. Non-metallic parts must not contain oils or greases and must be suitable for oxidizing environments. Assembly and testing must be carried out under strictly controlled, clean conditions to prevent contamination. Sour or wet H2S service. In environments with wet hydrogen sulfide or sour gas, materials must be compliant with standards for resistance to sulfide stress cracking. This includes body, trim, and pressure-retaining fasteners, regardless of whether they are directly exposed to the process stream. Material selection must align with ISO 1556 or equivalent specifications. Additional restrictions apply on hardness levels, heat treatment, and weld procedures to prevent embrittlement or failure in sour service. Heat transfer fluid service. Control valves used in high-temperature heat transfer oil or fluid service require robust construction and stable sealing under sustained thermal cycling. Globe or gate valves are preferred due to their predictable sealing surfaces and ability to handle thermal expansion. Metal seats are standard, and packing systems must tolerate elevated temperature without degradation. Bonnet extensions or cooling fins are sometimes required to isolate sensitive components from process heat. The valve must maintain leak-tight performance across frequent startup and shutdown cycles. Control valve actuator, design, sizing, and configuration. Actuators must be selected based on application-specific performance needs, installation geometry, and control philosophy. Where not otherwise specified, pneumatic actuators powered by instrument air are preferred for most services. Pressure-retaining components of the actuator must tolerate the maximum design pressure of the instrument air system. If this is not technically feasible, clear and permanent labeling must indicate the allowable pressure limit and must be approved by the principal. Actuators must include visible and durable travel indicators to show open-closed position. Indicators should be directly coupled to the actuator shaft and must use permanent markings with clear directionality, e.g., open, closed. Where applicable, color coding may be employed to indicate fail-safe status, such as red for spring close, green for spring open, subject to project specifications. Fail-safe action is mandatory for actuators associated with instrumented protective functions IPF at SIL 1 or above. In these cases, single-acting spring return designs are required. Where actuator size or torque prevents the use of spring return types, detailed justification with cost-benefit and space impact analysis must be submitted for principal approval. To prevent tampering, all mechanical linkages must be enclosed in protective housings. Rotating shafts, drive arms, and couplings must be designed for safety and weather protection. Actuator sizing and supply pressure considerations. Actuator sizing must ensure full valve travel within the specified stroking time, even under minimum instrument air supply pressure and maximum differential pressure. The actuator must be able to open or close the valve from any position, reseat and hold the valve in closed position against process pressure, maintain valve position under dynamic flow conditions. Sizing inputs, including thrust, torque, and spring range, must be based on the actual valve characteristics. Coordination between the valve and actuator manufacturers is essential to avoid oversizing, which leads to unnecessary structural support requirements and increased cost. If actuator or valve components cannot withstand full air header pressure, a pressure-reducing filter regulator must be installed upstream. For normal instrument air, a minimum design pressure of 4.2 bar gauge is assumed unless stated otherwise. When using local air buffer vessels, the lowest anticipated delivery pressure must be considered in sizing calculations. Maximum differential pressures used for sizing must assume worst-case process conditions. For forward flow, maximum upstream pressure versus atmospheric downstream. For reverse flow, maximum downstream pressure versus atmospheric upstream. Stroking time and response control. Standard stroking times for throttling applications are based on valve body size, ranging from 10 seconds for DN50 to up to 50 seconds for DN250. Valves above this size require stroking time specifications from the principal. Faster response times are necessary for applications like compressor anti-surge control and must be defined separately. If standard positioners cannot meet the response requirement, additional boosters or quick exhaust valves may be installed. For on-off service, e.g., shutdown valves, stroking time in each direction must be specified independently, especially where process safety or hydraulic shock is a concern. Controlled reopening is sometimes required to prevent surge or overpressurization. Material selection and construction. Actuator pressure housings must be constructed from either steel or anodized aluminum. Cast iron is not allowed for pressure components, but may be used for structural parts like the yoke. For IPF-rated valves, aluminum housings are not acceptable due to poor fire resistance. All actuator springs must be fully enclosed and corrosion protected. Sealing components such as diaphragms or pistons must be designed for low-friction operation and selected based on the actuating medium. For wet gas services, Buna N and other hydrocarbon-sensitive materials must be avoided. Actuators for variable pitch fans and dampers. When used with variable pitch fans or dampers, actuators must be single-acting spring return unless infeasible. Direct coupling to fan pitch or damper shafts is required, with no intermediate linkages that allow manual override unless explicitly approved. Airlines must be flexible to accommodate movement, and all components must be weather protected. Manual operation provisions, such as levers or gear-driven hand wheels, may be included for large actuators. These must be lockable and designed to prevent movement under load. For throttling dampers, positioners with custom characterization and air buffer vessels or lockup valves must be provided to ensure fail position retention. Electrical and hydraulic actuators. Electrical actuators are allowed only for on-off applications and must conform to applicable electrical standards. Use for throttling control requires explicit principal approval due to slower response and limited fail-safe options. Hydraulic actuators are typically used for specific services such as wellhead shutoff or loading arms and are outside the scope of general control valve specifications. Where used, they must comply with hydraulic system design and safety requirements. Control valve accessories, integration, configuration, and performance assurance. General integration approach. All accessories such as positioners, limit switches, air regulators, and solenoid valves must be supplied, installed, and tested with the control valve as a complete assembly. This ensures compatibility and allows full functional testing, including verification of stroking times and fail-safe action. Where physical layout allows, accessories may be installed on a separate mounting plate to ease valve maintenance and protect delicate components from mechanical stress. Accessibility requirements must be clearly defined in the requisition, including which sides of the valve will remain serviceable after installation. All accessories are considered part of the instrumentation package and must conform to instrumentation standards and quality requirements. Uniformity across projects and plants is critical for spares, maintenance, and reliability. Valve positioners. Electro-pneumatic smart positioners with a 4 to 20 milliamp input signal are the standard for modern control valves. These should be selected to match the plant's control system architecture and diagnostics capability. Where a control valve performance monitoring system is used or planned, standardization on a single make and model of smart positioner is preferred. If the valve supplier and positioner manufacturer differ, the valve supplier is responsible for ensuring correct configuration of positioner settings, including travel range, control characteristic, and split range behavior if applicable. For split range setups, each valve should receive a full 4 to 20 milliamps input from the control system. Positioners must be weatherproof to at least IP55 and must not include bypass valves. Capacity must be adequate to charge and vent actuator chambers within the required stroking times. Positioner output tubing must be properly sized, minimum 6 mm OD, and material must be compatible with environmental exposure. Stainless steel tubing is mandatory for offshore, corrosive, or H2S environments. All compression fittings must be uniform in type and size across the facility. Each positioner must carry a clearly visible tag plate indicating input signal range and supply pressure. Hand wheels. Hand wheels are only included where specifically required by operations for manual override. If provided, they must not obstruct automatic valve movement and must disengage cleanly. Declutchable hand wheels must include an instruction plate and locking system to prevent unintentional engagement. Design must comply with applicable mechanical and safety standards. Mechanical limit stops. Mechanical travel stops must be fitted to the actuator or valve to prevent over-travel. These must be externally adjustable and fitted with tamper-resistant locking mechanisms. Screws tapped directly into the valve body are not permitted for this function. Stops must be set precisely during assembly and protected against accidental disturbance. Air lockup valves. Lockup valves are mandatory where valves must maintain last position upon loss of instrument air. These are especially critical for double-acting actuators or IPF services without spring return. Settings must be 0.5 bar above minimum actuator operating pressure and locked against adjustment. In positioner-equipped systems, lockup valves must be installed between the positioner and actuator. In systems using solenoids, the solenoid must be installed downstream of the lockup valve to preserve air retention. Limit switches. Limit switches must be of the non-contact proximity type, enclosed for mechanical protection, and terminated in a sealed junction box. The box must meet the hazardous area rating where installed. External linkages must be shielded, and the switch mounting must follow the manufacturer's recommended installation geometry. Each switch must be independently adjustable and provide unambiguous indication of valve position. For SIL-rated IPF duties, the switch assembly must be of fail-safe design. Where both fail-safe and non-fail-safe switches are used on a project, fail-safe types must be reserved for safety-critical circuits. Instrument air buffer vessels. Buffer vessels are required where actuators must maintain or achieve a safe position during air supply loss, especially for springless designs. There are two types: secured instrument air vessels. For safety or shut down critical functions, must allow at least 3 full valve strokes within 30 minutes, assuming 4.2 bar initial pressure. Standard buffer vessels for non-critical applications may follow manufacturer sizing guidelines, but must still meet stroke and time requirements. All designs must be reviewed and approved by the principal. Safety relief devices and pressure gauges must be included where applicable. Air lubricators. Lubricators may be installed for long-stroke pneumatic cylinders. These must be oil mist types with external fill capability, visible level indication, and a 1-month refill interval under normal use. Glass bowls are not permitted. Where solenoids are also present, the lubricator must be located upstream of the solenoid valve. Solenoid valves. Solenoids used for control valves must have resilient seats for TSO performance and flow capacity sufficient for required stroking speed. Where solenoid capacity is inadequate, quick exhaust valves should be added to ensure performance without requiring high-power solenoids. To prevent clogging in freezing conditions, solenoid exhaust ports must use downward-turned open tubing rather than sealed covers. Shunt diodes must be installed across DC coils to suppress voltage spikes. For positioner-based systems, solenoids must be located between the positioner and actuator. Direct-acting solenoids are preferred. For large actuators, solenoid-operated pilots controlling external pneumatic switching valves are preferred over pilot-operated solenoids for robustness. Internal pilot sourcing is not allowed. Filter regulators. When valves cannot tolerate full instrument air header pressure, a filter regulator is required. These must be of the reducing relief type, self-draining when mounted vertically, and fitted with rigid filter elements, maximum 40 micrometers. Glass bowls are prohibited. Pressure gauges must be installed to monitor inlet and outlet pressure. Standalone filters. If pressure reduction is not required, a standalone filter may be used instead of a regulator. These filters must match the construction and performance criteria of regulator filters and include inlet-outlet pressure indication. Quick exhaust valves. These valves accelerate stroking for on-off services, but should not be used in throttling applications due to control instability. They must be mounted directly on the actuator port. Avoid pilot operation and use open-ended drain tubing to prevent clogging in cold weather. Volume boosters. Volume boosters may be installed to meet fast stroking requirements where positioner capacity is insufficient. Use is limited to control circuits where responsiveness is critical and must be coordinated with actuator sizing. Flow restrictors. For slow opening or slow closing functions, electronic control via DCS is preferred. Where mechanical restrictors are used, typically for on-off valves, they must be lockable and clearly marked with flow direction. Careful placement is required in relation to solenoid valves to ensure the restrictor only affects the desired travel direction.